Hi, good morning, everybody. This is Dr. G. Amarendra Rao, Professor of Mechanical Engineering, Vijnana Bharati Institute of Technology, Hyderabad. In today's session, we'll discuss about combined modes of heat transfer and composite systems. First, let us see what the meaning of combined modes of heat transfer. In many engineering applications, we will come across more than one mode of heat transfer simultaneously. Such problems are termed as combined modes of heat transfer. In such cases, there would be basically conduction subjected to convective or radiative or both the environments. For instance, in the design of a furnace wall, we need to consider all the three modes of heat transfer. In the sense that conduction across the wall, convection on the surface due to inside hot gases and outside cold air. Further, in view of very high temperatures of furnace gases, radiation also becomes predominant. So these problems can be conveniently analyzed by electrical analogy. Now we shall introduce the concept of overall heat transfer coefficient. So that also will be featuring. Therefore, we will be using both electrical analogy and the concept of U in understanding these complex situations. First, let us formulate the problem. Let's imagine we have a wall of some thickness L made up of some material having thermal conductivity K. And left side we have very high temperature gases involving inside radiation, inside convection. And whatever heat that is reaching the left side surface by radiation and convection will be conducted along the thickness of the wall, Then whatever heat that is reaching the right side surface will be going away partly by radiation and partly by convection. And I would like to reiterate that still we are talking about 1D steady state heat transfer. And for any system to be in steady state condition, energy coming in must be energy going out. They must be equal. Therefore, inner radiation, inner convection will be conducting, and whatever heat that is reaching here by conduction will be going out by outer radiation and outer convection. Mathematically, the situation will be given like this. Inside we have a fluid at HRI, HITI, indicating inner radiation, inner convection, and inside fluid temperature. Outside we have HR0, H0, T0. So outside radiation, outside convection, and outside fluid. And we claim that Ti is highest, followed by T1. T1 is the left side surface temperature, followed by T2, which is the right side temperature. Then T0 is the right side fluid temperature. And here the terminology is HRI is the inner radiative heat transfer coefficient, HR0 outer radiative heat transfer coefficient, HI inner convective heat transfer coefficient, H0 outer convective heat transfer coefficient. So analogous to H, we are introducing something called HR. And the corresponding circuit diagram looks like this. Since radiation and convection are happening simultaneously, the corresponding resistances will be acting in parallel between Ti and T1. Then there is going to be conduction. Again, there is going to be outer radiation, outer convection occurring simultaneously, therefore two parallel resistances. It may be noted that R1 is inner radiative resistance, R2 inner convective resistance. So R1, R2 are the inner radiative and inner convective resistances. R3 is the conductive resistance through the wall. Then R4 and R5 signify outer radiative and outer convective resistances. And we simplify this circuit by using the famous Ohm's law that whenever two resistances are working in parallel, or for that matter, whenever number of resistors are working in parallel, the reciprocal of their equivalent resistance will be equal to sum of the reciprocals of individual resistances. As a result, R1 and R2 can be replaced by R12, that the equivalent resistance of R1 R2. R3 will be carried forward. Then R4 5 is the equivalent resistance of R4 and R5. Now that we have all the resistances working in series, R12, R3, R4, 5, again we recollect Ohm's law that whenever your number of resistances operating in series, their equivalent resistance will be sum of the individual resistances. So R equivalent obviously will be R12 plus R3 plus R4, 5. And nomenclature already I was talking about. R1 1 by HRIA is inner radiative resistance expressed in degree centigrade per watt. R2 1 by HIA is inner convective resistance. This is HI. Then R3 L by Ka conductive resistance. R4 1 by HR naught A outer radiative resistance. Then R5 is 1 by H naught A, that is outer convective resistance. And already I was talking about these terms: HRI, HR naught, inner radiative, and outer radiative, inner radiative heat transfer coefficient. Then H naught is inner convective heat transfer coefficient. Then L thickness of the wall, K thermal conductivity of the wall, A is surface area of the wall material. There's a small correction here. This is obviously HI. Inner radiative heat transfer coefficient, inner convective heat transfer coefficient. Then HR naught, outer radiative heat transfer coefficient, H naught, outer convective heat transfer coefficient. So again, Ohm's law, I was talking about it, separately synthesized. When you have R1, R2 working in parallel, then 1 by R12 is 1 by R1 plus 1 by R2. So their equivalent resistance, if you simplify, will be the product of their individual resistances upon the sum of their resistances. So obviously you can find out Q as delta T by R equivalent. So R equivalent will be R12 plus R3 plus R45. Already this has been discussed quite elaborately. And once you get this, you can always go ahead with the calculation of temperatures. Then you can go ahead with the calculation of rest of the parameters as described in these simple equations. And when you have two resistances working in parallel, uh, the sum of their individual resistances will give you the equivalent resistance. So this is how we deal with a general problem involving both radiation and convection. Now we can always calculate the breakup, how much is radiation, how much is convection. Radiation will be T1 minus T2 by R1, then convection will be T1 minus T2 all right by R2. So that way you can always find the breakup, and by energy balance total heat transfer will be inner radiation plus inner convection. And this already I have told you, Q1 is T1 minus T2 by R1, Q2 is T1 minus T2 by R2. Then many of the times we may not really bother much about the radiation, leaving only inner convection, outer convection. Therefore, no parallel resistances. Your corresponding circuit diagram will have only resistances operating in series. R1 is inner convective resistance, R2 is conductive resistance, R3 is outer convective resistance. Then R equivalent will be sum of the individual resistances. Now you can find Q as del T over all by R equivalent. Then this R1, R2, R3 already told you, inner convective, conductive and outer convective resistances respectively. So that's how you define combined modes of heat transfer. Now this concept can be imposed on composite systems. Like a composite system is made up of number of materials. So in many engineering applications, we would be using composite systems in order to fulfill diversified requirements of the given application. Typical examples will be furnace walls, then steam pipes, nuclear reactor vessels are some of the very popular examples. Now we shall look at the following types of composite systems with only convective environments. We are talking only about convective environment. But whenever radiation is there, we can always take care of it. First, we'll talk about composite walls. Walls arranged only in series, walls arranged only in parallel, then a combination of series and parallel. Then we will ponder over composite cylinders followed by composite spheres. So these topics will be discussed in some of the sessions beginning from now. First we'll see composite walls with walls in series with convective environment, of course. So we have a composite wall made up of 3 layers, thicknesses L1, L2, L3, materials K1, K2, K3. Inside environment HITI, then outside environment H0, T0. Now we have a couple of objectives. First objective is to obtain an expression for Q in terms of given data. Then to get interface temperatures T1, T2, T3, T4. And in order to have continuous heat transfer at a steady rate, we claim that Ti is ultimate highest, T0 is lowest. In the middle, we have T1, T2, T3, T4. They are the surface temperatures. Then this problem can be easily done with electrical analogy involving number of resistances. That will be obviously 1 plus n plus 1. One is inner convective, last one is outer convective. So you begin your journey with convection, end with convection. In the middle, number of conductive resistances, as many as the number of layers. Since we have begun our proposal with a 3-layered system, we are going to have 3 conduction resistances. Like R1 is inner convective resistance, R2, R3, R4 are the conductive resistances, R5 the outer convective resistance. Since all these resistances are working in series, blend them together to get your equivalent thermal resistance. Now Q becomes simply overall thermal potential Ta minus T0 by R equivalent. You can see by way of this concept overall thermal potential, we are able to eliminate the unknown temperatures T1, T2, T3, T4. Now, R equivalent is sum of the individual resistances. Then R1 is inner convective resistance, already I told you, 1 by HIA. R2 L1 by K1A, conductive resistance of layer 1 of thickness L1, material having thermal conductivity K1. R3 is conductive resistance of second layer, thickness L2, material K2. R4 conductive resistance of by third layer of thickness L3, material K3, and so on. So these particular conductive terms are fragile. You can have as many as you wish, beginning from 1, and you can go on up to 3, 4, 5, 6. If you imagine one more layer, the corresponding resistance would be L4 by K4A. And at the end, you are going to have outer convective resistance that is given by 1 by H0A. Then you can find Q as del T overall by R equivalent. Because of steady state conditions, whatever heat that is getting convected from inside fluid to inside wall, from fluid to wall should be conducted in the first layer. This must be conducted in the second layer. This we call it as energy balance. Therefore, once we get Q using this formula del T overall by R equivalent, we can as well write this Q as inner convection Ti minus T1 by R1. From this we can find T1 as Ti minus Q into R1. Then Q is also conduction through first layer T1 minus T2 by R2. You can find T2, and so on till you get all the intermediate temperatures. So this is how we calculate intermediate temperatures as well as heat transfer rate. Now R equivalent, already I told you, R1 plus R2 and so on. You can take 1 by A common. This becomes 1 by HI plus L1 by K1 and so on till you get the outer convection term. And these conduction terms are fragile, they are expandable. Therefore you can write this as 1 by A times 1 by HI. You begin with convection. At the end 1 by H0, you end with convection. In the middle, sigma Lj by Kj, where J is equal to 1, 2, 3 and so on. So you can have as many J terms as you feel. Number of layers can be as per your convenience. Then obviously Q would be del T by R equivalent. And if you incorporate this, you are going to get a very general expression for your heat transfer rate in a composite wall made up of number of materials arranged in series. Now one can float the concept of overall heat transfer coefficient, which represents the heat transfer rate per unit area per unit overall thermal potential. Mathematically, U is Q by A del T overall, or Q can be written as UA del T overall. So based on this equation 3, we can redefine overall heat transfer coefficient as a mathematical parameter, which is so defined that when it is multiplied with the product of area and overall thermal potential, we are going to get the heat transfer rate in the system. Now Q is available in equation 2 in terms of basic data, and Q is available in equation 3 in terms of U. And when you compare these two equations, we are going to get the general expression for your overall heat transfer coefficient as 1 by U is equal to 1 by Hi plus sigma J is equal to 1, 2, 3 and so on, Lj by Kj plus 1 by H naught. If you talk about the current system, a 3-layered system, J will go on up to 3. So 1 by U will be 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. So in the middle you are going to have 3 conduction terms equivalent to 3 layers you are talking about. The simple logic shows that U and R equivalent are dependent variables, and when you compare equations 1 and 4, you can show that UA R equivalent is equal to 1. So if I got U, that is overall heat transfer coefficient, it as good as you have R equivalent, and vice versa. Or we can say that R equivalent is inversely proportional to U for the given area. In a similar way, one can imagine a system where number of walls are placed one over the other, walls in parallel, like this particular diagram illustrates. Then inside convection, outside convection, in the middle number of walls arranged in parallel. Maybe 3 walls we have taken having areas A1, A2, A3 made up of materials of thermal conductivities K1, K2, K3. Of course, all the walls have same thickness. When you have walls in series, all the walls will have same area. Area is common for all the walls, right? This area. Thicknesses will be different. But here, thickness will be the same, but areas will keep on changing. And when you add all these areas, A1 plus A2 plus A3, you are going to get total area of the wall. Now whatever heat that is getting convected from inside fluid to inside wall, which is at temperature T1, it will be split into number of components, as many as the number of layers. Q1 is the upper component, conducting through first layer, L, A1, K1. Q2 is the middle component, getting through the second layer, L, K2, A2. And Q3 the third component, getting through same thickness, A3, K3. And all of them will come and join here. Energy balance reveals that heat transfer rate Q will be equal to Q1 plus Q2 plus Q3. And whatever heat that reaches the right side surface will be going away by convection to the fluid H0, T0. So this is the physical arrangement. And electrical analogy reveals that these 3 resistances are going to operate in series, in parallel. First R1, inner convective resistance, then 3 conductive resistances operating in parallel, then outer convective resistance again operating in series. Now this R2, R3, R4 can be replaced by their equivalent resistance R2, 3, 4. Now that you have everything operating in series, add them together, you are going to get the equivalent resistance, which is R1 plus R2, 3, 4 plus R5. Now R1 is inner convective resistance, already we have introduced. R2, R3, R4 are the conductive resistances, thickness is same. materials and areas are different. R5 is the outer convective resistance. Then R234 is the equivalent resistance of R2, R3 and R4. And by Ohm's law, the reciprocal of the equivalent resistance will be sum of the reciprocals of individual resistances when they are working in parallel. Now your R equivalent is sum of the individual resistances R1 plus R234 plus R5. Now you can calculate Q as delta T overall by R equivalent. Q is available. Now having found Q, you can make the energy balance. Q is equal to Ta minus T1 by R1. This will give you T1. Q is also equal to T1 minus T2 by R234. This will give you T2. And once you know T1 and T2, the surface temperatures you are able to find by using this simple logic. Now your Q1 upper component will be T1 minus T2 by R2. Your middle component will be T1 minus T2 by R3. Your lower component will be T1 minus T2 by R4. That way you can find the conduction components which are shown over here. Glide is same, potential is same, only resistances are changing depending upon the area available and the material. Now one can combine both these concepts to get a very general situation of composite walls in series parallel combination. In series parallel combination, you can see series you have three thicknesses L1, L2, L3, and first layer of thickness L1 is split into two parts A1, K1, A2, K2. Second layer has got three parts A3, K3, A4, K4, A5, K5. Third one again we have taken two components A6, K6, A7, K7. Total area A will be equal to A1 plus A2, right? A3 plus A4 plus A5 and also A6 plus A7, conservation of area. Q will be again Q1 plus Q2, upper plus lower. Q3 plus Q4 plus Q5, upper plus middle plus lower. And of course Q6 plus Q7. So whatever heat that is reaching by convection to this left side surface will be split into two parts, upper part, lower part. That's the meaning of Q1, Q2. And whatever heat that reaches the intermediate surface will be split into three parts, Q3, Q4, Q5. Like that you are going to have energy analysis. No one can have the corresponding circuit diagram. Convective resistance, two conductive resistances in parallel, three conductive resistance in parallel, two conductive resistance in parallel, again outer convective resistance. Q is steadily going on from left side Ti to right side T0. Of course, this is T0, the lowest temperature in the system. This is T0. Then this Q is undergoing various manipulations. You can see now first you replace R2, R3 by R23, R4, R5, R6 by R4, 5, 6, R7, R8 by R7, 8. Now you have everything operating in series. R equivalent will be R1 plus R2, 3 plus R4, 5, 6 plus R7, 8 plus R9. Now you can define all the resistances as per the standard format. Beginning with convection, ending with convection, in the middle number of conductive resistances. Right, then R2 3 is 1 by R2 plus 1 by R3, R4 5 6 is 1 by R4 plus 1 by R5 plus 1 by R6, 1 by R7 8 is 1 by R7 plus 1 by R8, then R equivalent is R1 plus R2 3 plus R4 5 6 plus R7 8 plus R9, then Q is del T overall by R equivalent. By making energy balance you can get to know the surface temperatures T1, T2, T3, T4. Then by knowing surface temperatures, you can get to know the breakup, upper component, lower component, upper component, middle component, lower component, upper and lower components. That way you can make a complete analysis of what exactly you have done in this very general composite systems. Walls in series, walls in parallel, series parallel combination. So with this we'll end this session. In the next session we'll try to look at some numericals on composite walls exclusively.